Hi everyone. So in this video, we're going to be talking about how to solve a logarithmic equation. So this is a very simple example of a logarithmic equation, but they'll generally look like this. So whereas in the last video, we were solving equations where the variable was in the exponent, in this video, the variable will be within a logarithm. So I think in general, most people probably find logarithms a little bit more kind of complicated than exponentials, but I actually think that solving logarithmic equations is even easier than solving exponential equations. And the reason for that is that in general, when we're solving a logarithmic equation, all we really need to do is use the definition of a logarithm to rewrite it in an exponential form. So let me kind of write that down and then we'll get to that first example. So to solve a logarithmic equation, we're going to use the fact that log base b of a number x is equal to another number y. That is equivalent to saying that that same base b raised to the y is equal to x. Right? That's our definition of a logarithm, because remember, logarithms are asking you what exponent you need to raise this number to get this number, and the answer is this, right? So the answer to the logarithm is your exponent, so that's there. The base is the same, so that's here. And then the number that you get when you raise the base to that power, well, that was the number inside your logarithm. So we're going to use this fact to rewrite the equation in exponential form. And we'll see that that will put the variable somewhere where we can easily solve for its value. Okay, so let's start with a very simple example. So in this first equation, we have log base 3 of x is equal to 2. So this is one that I think you might even be able to just kind of figure out by looking at it, right? So one thing that I mentioned, I try to mention this all throughout the class, but especially in the last video, I reminded you how solving an equation just means finding the values that make it true. So you may be able to think of, what would that number of, what would x need to be in order to make this a true statement? But if you do it in your head, what you're really relying on is this definition up here. So let's go ahead and just take this logarithm and rewrite it in that second form. So if we rewrite it in that second form, we would be saying that 3 squared is equal to x. And so what is 3 squared? 3 squared is 9, and so our answer is x is equal to 9, and that's it. And that makes sense, right? Because log base 3 of 9 is equal to 2. So again, this is one that you may have just been able to look at and kind of come up with the answer. But as we get into more complicated examples, I think having this skill of being able to rearrange the logarithm will be really useful. So let's look at another example. So this one says ln of 25 minus x is equal to 3. Let me just actually scooch this up a teeny bit to give us a little more space. Okay, so let's do the same thing we did in the last one and rewrite this in that exponential form. So remember that for ln, the base is e. And so we have e raised to the third power is equal to 25 minus x, right? Because the 3 is our exponent, and then e raised to the third power is supposed to give us the value inside of the logarithm. Okay, so from here, we just need to solve for x, right? And so how can we solve for x? Well, there's a few things we could do. Personally, I prefer to try to get the x on the side so that it becomes positive. So I would probably prefer to do this by adding x to both sides. So if we add x to both sides, we now have x plus e cubed is equal to 25. And then we can subtract e cubed from both sides. So we get x is equal to 25 minus e cubed. And by the way, you could have also subtracted 25 from both sides and then divided both sides by -1. You would get the exact same answer. Okay, so this is actually our answer, right? This is in exact form. So remember that e is an irrational number. So if you try to type it into a calculator, you're going to get an approximation. And so if you want to have an exact answer, you would need to actually just leave it like this. So this, even though it kind of looks like you're not done, right? This doesn't necessarily look like it's a number. It is. E is a number. E cubed is a number. So 25 minus e cubed is a number. And so this, like I said, this would be our exact answer. And then if you wanted to find your approximate answer, you could type this into a calculator and you would find that it's approximately 4.91. So that is our approximate answer. Okay, so let's do one more that's kind of this straightforward type, and then we'll do a couple of other examples that have a little bit more going on. Okay, so this one says log base 2 of 2x plus 3 is equal to 0. So I find that it's very easy to mix up having an exponential equation versus a logarithmic equation equal to 0. So one thing that we saw in our last video is that when you have an equation of the form, a to the something, some expression, it doesn't have to just be x, it can be, whatever. If you have an equation that looks like this, that would have no solution. So, we saw an example of that in our last video, but just to write another example, I'm talking about something like 2 to the 3x plus 5 is equal to 0. That would have no solution because you can't take your base and raise it to an exponent and get 0. But that's not what this equation is saying, right? This is not saying an exponent, a number raised to an exponent is 0. This is saying the value of a logarithm is 0. So before we jump to the conclusion that this has no solution, let's try to actually rearrange it the way that, that we're doing these questions. So our base is 2, our exponent is 0, and then our answer to the exponential should be 2x plus 3. And so this tells us that 1 is equal to 2x plus 3. So there actually is going to be a solution. So you can evaluate a logarithm and get 0. And then the times that happens is when the stuff inside the logarithm is equal to 1, right? A logarithm of 1 is equal to 0 because what power do you raise a number to get 1? You raise it to the 0 power. So that's where this idea comes from. It comes from the fact that in order for the answer to a logarithm to be 0, the stuff inside the logarithm has to equal 1. Okay, so from here, we can just isolate x. So we can subtract 3 from both sides and we get negative 2 is equal to 2x. And then we can divide both sides by 2, and I'll just flip the order of things and say x is equal to negative 1. So you could check your answer to this, right? You could plug it back in. So what happens if we plug in negative 1? We would get 2 times negative 1, which is negative 2, plus 3, which is 1. So log base 2 of 1 is equal to 0. It checks out. So I just want to kind of finish what I wrote over here. A to something equals 0, that has no solution. But in general, when you have a logarithm of, some expression equal to 0, that does have solutions. I should say, does have a solution. So just kind of a side note. I think it's just very tempting to look at this equation and think it's not going to have a solution, but it does. Okay, so I want to now look at an example where we have to isolate the logarithm before trying to write it in exponential form. So this is actually just like something we saw in the last video, right? We saw that when we're using the methods for solving exponential equations, we want to first get the exponential part isolated before we go and do any of those methods. And so it's the same idea here. We want to get this part, just the logarithm, just log of 2x. We want to get that by itself. So we need to kind of just peel back all the layers, subtract away whatever needs to be subtracted, divide whatever needs to be divided. So we can start by subtracting 4 from both sides. And so that will give us 3 times log of 2x is equal to 12. And then we're still not completely isolating the log yet, right? We have to still divide both sides by 3. So if we divide both sides by 3, we get log of 2x is equal to 4. Okay, so now we're ready to rewrite this in that exponential form. We have to remember that when we have just log, that's a log with a base of 10. And so when we rewrite this in our exponential form, our base is 10, our exponent is 4, and that should be equal to 2x. So 10 to the 4th power is going to be 10 with 4 zeros. Is that 4 zeros? Yes, I think it is. So 10 with 4 zeros is equal to 2x. And so now to isolate x, we just divide both sides by 2, and we find that x is equal to 5,000. And if we were to go back, you could go all the way back to the beginning and plug it in, but you could also try plugging it in here, right? So if we did log of 2x, that would be log of 10,000. And that's asking you what power you have to raise 10 to get 10,000, and the answer is 4. So that, again, checks out. All right, one last example. So this is a slightly more, has a little bit more going on kind of example. So this is a case where we have multiple logs in our equation, right? We're adding together 2 logarithms, and we have that equal to 1. So in a situation like this, we really only have a rule for going between exponential and logarithmic form when your original equation looks like the one on the left, right? We don't have something that's like log plus another log. So we need to find a way to take this equation with multiple logarithms and combine it into only one logarithm. And so fortunately, we have a rule for that, right? We know that if you have 2 logarithms with the same base, and you're adding them, well, that's the same thing as doing the logarithm of their product. Right? So let me maybe make a note of that so you can see where this is coming from. So from here, we're remembering the fact that log base b of x times y is the same as log base b of x plus log base b of y. And we're using it in the kind of backwards direction, right? We're starting with the addition and we're going from here to here. Okay, so how do we go from here? Well, now we're in the same kind of situation that we were in the other ones. And we might as well multiply this part out, the x plus 2 times x minus 1. So let's just go ahead and do that so we have it multiplied out. So we have x plus 2 times x minus 1. That's going to give us x squared plus 2x minus x. So that's plus x, and then minus 2. Okay, so now we're ready to rewrite this in exponential form. So just like in the last one, we have a base of 10. So that means that we, in this case, have 10 to the 1 is equal to x squared plus x minus 2. In other words, if you're taking a log with a base of 10 and the answer is 1, that means the stuff inside had to be equal to 10, right? 10 to the 1 is 10. Okay, so how do we go from here? Well, remember in general, when you're solving a quadratic equation, you generally want to get it set equal to 0 because that's where you can take advantage of factoring or the quadratic formula. You can't do those things until your equation is equal to 0. So we want to start by subtracting this 10 to the other side. So if we subtract 10 from both sides, we get 0 is equal to x squared plus x minus 12. And so now that this is set equal to 0, you can either use the quadratic formula or factor. This one can be factored, so let's go ahead and factor it. So what would give us a negative 12 and a plus x? Well, we could do that with x plus 4 times x minus 3. And so this gives us 2 solutions. We have either x is equal to, or let me write it kind of the longer way, x plus 4 is equal to 0, right? If we have 2 things multiplied together equaling 0, one of them has to be 0. So that gives us these 2 equations. And from there we get x is equal to negative 4 and x is equal to positive 3. So there's one kind of complication in this problem that we need to go take care of. So because our original equation was not exactly the same form as the equation that we eventually ended up solving, we need to check whether both of our solutions can actually be plugged into the original equation. So the issue is that you cannot take a logarithm of a negative number. And so we just need to make sure that when we plug these two values into our original equation, that we're not actually taking a logarithm of a negative number. So that's something that's called an extraneous solution. So sometimes when you're solving an equation, you kind of do an operation that might introduce new solutions that didn't kind of fit with the original equation. And so that's really all we have to do here is just check that those both work. So we're going to check. We're going to take each of these numbers and plug them into our original equation. So just to remind you, the original equation was log of x plus 2 plus log of x minus 1 is equal to 1. And so we just need to check that when we plug these inputs in that it makes sense. So for the first one, x is equal to -4. If we plug that in, we get log of -4 plus 2 plus log of -4 minus 1 is equal to 1. But this we can already see is going to give us an issue, right? Because we'll have log of -2 plus log of -5. And this is just not a valid equation. You know, it doesn't even really make sense to check whether this equals 1 because both of these are actually undefined. So going back to when we first started talking about logarithms, you cannot take a logarithm of a negative number. I know there's like a lot to juggle with like negative or 0 or all the exponents, logarithms, you know, whether we're talking about the input or the output. Let's just pause for a second and remember what logarithms mean. So what does log of -2 mean? Log of -2 is equal to an exponent, right? It's the exponent that you would need to raise 10 to get -2, right? That's like the definition of log of -2 is the number that you need to raise 10 to get -2. And there is no such number, right? You can't raise 10 to a power and get -2 as your answer. That just doesn't work. And then similarly, the second one would be saying, what power do you need to raise 10 to get -5? Again, that doesn't make sense. And so what this tells us is that x is equal to -4 is not actually a solution. And what's really going on is that it is a solution to this equation. Once we combine them into a logarithm, basically what happened is that because now we're multiplying these two different pieces together, it's getting rid of that issue of negative numbers, right? Because if you multiply, here we plugged in, here we got -2, right? And here we got -5. Well, then you plug them in or you multiply them together and you get a positive result, so it works. But when the equation was in its original form, it doesn't work. And so we have to go with our original form and say, sorry, that actually is not a real solution to our problem. So hopefully that makes sense. Let's try the other one. So the other solution that we found was x is equal to 3. So let's check out what happens when we plug in 3. So for 3, we would be getting log of 3 plus 2 plus log of 3 minus 1. And that's going to give us log of 5 plus log of 2. And it's not super obvious to see that this answer is going to be 1, but if you were to plug this into your calculator, you would see that it is 1. And you could also think of this by doing the combination, right? If you did log of 5 times 2, that would be log of 10, and that is equal to 1. But the important part, when you're checking your answers, it's really not so important to check that you actually get the correct answer. I mean, that doesn't hurt. That's always a good thing to do. But the thing that you need to be on the lookout for is whether you get a negative result inside the logarithm when you plug that number in. Because again, when we did that kind of combination rule, we somehow we made it so that negative solutions were possible when they really weren't possible in the original format. And so this works out. This is fine. You know, these are both defined. There's no issue. We're taking logarithms of positive numbers. And so that this tells us that x equals 3 is the solution. It's actually the only solution to our equation. So this is not something that's going to come up a whole lot. Like I said, this only comes up if we are solving a equation where we end up using a logarithm rule to combine things. And the only extra step you have to do is just, again, plugging in your results and making sure that you don't get a negative inside of your logarithm. All right, so that is it for this video. In our next and final video for the quarter, we'll be talking about applications of exponential functions. So we'll see that exponential functions can be used to model a lot of different phenomena in the world, in the real world, and we'll get to see some of those different applications and kind of apply some of the things we learned about solving exponential equations as well. So I'll see you all in the next video.